Hello, y'all. Welcome to lesson 106 in my DP chemistry series. Today we're going over reactivity 3.4.6. This is an HL topic. We're going to be talking about how a Lewis acid is an electron pair acceptor and a Lewis base is an electron pair donor. And we'll be able to apply Lewis acid-base theory to inorganic and organic chemistry to identify the role of the reacting species. So we've learned quite a bit about acids and bases thus far, but something that we don't often see is that metals can act acidic when placed in water, which is kind of weird because they don't have protons to donate. No protons to donate. And this kind of contradicts our idea of acids and bases when looking at the Bronsted-Lowry acid-base theory. And so what we have to do is start looking at the Lewis acid-base theory. And we can use this theory to explain all acids and bases, including Bronsted-Lowry acids and bases. And the thing is, this fully depends on the interactions of electron pairs. So Lewis acids fully depend on looking at how electrons move and are donated and accepted. So returning back to our Bronsted-Lowry, which I'm just going to abbreviate BL, that is H plus donating or accepting. So we have to be looking at the movement of protons. And so generally we can see this in an example if we take hydrochloric acid, which is our donor, and we know it's our donor because it has donor, and we know it's our donor because it has the hydrogen. And it's going to donate to our H2O, our water, which is our acceptor. And we know in this reaction we get hydronium, HAO plus a chloride ion, Cl minus. And we can see that this hydrogen ion has moved into water to create our hydronium. So this follows our general knowledge of acids and bases, but we can observe this from the perspective of electrons. So let's look at the actual electrons. So first we need to recognize that oxygen in water is partially negative. So we're looking at partial charges now, and this is going to attract the hydrogen in HCl, which will cause the covalent bond to break. And that's within HCl. And chlorine will accept both electrons from the bond because it is a more electronegative species. So what does this actually look like? Well, I'll use Lewis diagrams, which are great to describe Lewis acids and bases as a way to demonstrate this. So when looking at this, we have our water plus our hydrochloric acid. We'll denote that hydrogen is partially positive, chlorine is partially negative, and for the most part, I'm just going to look at the oxygen here as partially negative. Specifically, these electrons, what's going to happen is we're going to see them attract that hydrogen. And the electrons in this bond will then shift all the way to the more electronegative chloride or chlorine, which will become chloride. Thus, our reaction ends up looking like this, where we have hydronium with a positive charge plus our chloride with a negative charge. And there we have it. This is looking at it from the perspective of the electron movement or electron pair donation and accepting. So we can really say that we are demonstrating electron transfer in reactions. So instead of looking at proton transfer, we're now looking in terms of electron transfer. So our basic idea of Lewis acid-base theory is that first our bases donate electron pairs. So in this case, our water, the oxygen in our water, and the acids accept electron pairs. In this case, the hydrogen in hydrochloric acid. Generally, when we're looking at our different acids and bases, we have some common Lewis acids that are good to keep in mind. The most common one is going to be H plus, the proton. It wants to accept electron pairs. We also have metal cations. Metal cations are where we need to use Lewis acid-base theory to explain their acidic behavior, as well as D block cations. So things like silver. Now, when we look at a Lewis acid-base reaction, generally what we're looking at is our acid plus our base with its electron pair, and that electron pair is going to attract. So this is our acid, this is our base. And when they bond, we get a B. And what you might note is that this is a coordination bond. Both electrons are being donated from one species. So an example where we can see this is in aluminum chloride reacting with water. So solid aluminum chloride can react with three waters. And what we'll notice is that aluminum will go ahead and form aluminum hydroxide, producing 3HCl aqueous. And so this is an example where we can see aluminum going through a Lewis acid-base reaction. Now, we talked a little bit about common Lewis acids. We have also some common Lewis bases. Those are going to be water, as we saw in the HCl reaction, ammonia. We also can look at hydroxide ions, cyanide ions, halide ions, so any of our halogens, and things like ethanoate ions. And we're going to look at that as we look at organic Lewis acid-base reactions. Generally, when we look at Lewis bases, what we're looking at are electron-rich species. These are generally negatively charged, but not always. I'll say mostly. You can see that from our hydroxide, cyanide, halide, and ethanoate ions. And so they're going to have that electron pair to form that covalent bond. Electron pair available to form coordination, covalent bond, which will just make them able to do that. So when we look at Lewis acids and bases, we generally have two scenarios that we're looking at this. So we'll generally look at them in inorganic versus organic scenarios. So starting with inorganic, because we've already explored that a little. In inorganic scenarios, what we're generally looking at is metal cations acting as acids, as we explained earlier. And so when we look at that, they're going to have their positive charge, which will be there available to accept the electron pair. This gets more complicated and a little more interesting when we're looking at organic reactions. And we'll explain this much further down the road as we go into organic chemistry. But what we're going to be looking at are carbocations which are what they sound like, carbons with a positive charge, or carbonyl compounds. Generally, carbonyl compounds are some type of carbon chain attached to a carbon with a double bond oxygen, and then maybe another carbon chain or a hydroxide or a hydrogen. So carbonyl compounds, we'll explain why that is. And these act as Lewis acids as well. The reason carbocations act as Lewis acids is because they're cations. Much like metal cations, they will act as an acid attracting the electron pair. Carbonyl compounds are a little more interesting because what we actually notice is that the oxygen is so electronegative and the carbon is um, so much less electronegative that it forms a positive partial charge, which can therefore be the jumping off point to act as a Lewis acid. That carbon generally, so both of these create what we call electron deficient carbons. And as they're electron deficient, they will accept electron pairs. These will usually come from hydroxides or alcohols, which alcohols are just an OH bonded to a carbon group. So they're both OHs. Hydroxides are, as we know, ions floating freely, but alcohols are just a carbon bonded to an OH. So this is the main defining factor that we can start using Lewis acid bases in when we're talking about metal cations as well as organic carbon species that are deficient in electrons. The last part of this unit that I just want to highlight is that all Bronsted-Lowry acids and bases are Lewis acid bases. They're all Lewis acid bases. However, not all Lewis are Bronsted-Lowry. So it only works one way. So as you start exploring different acids and bases, keep note of which ones are Lewis but not Bronsted-Lowry and which are both. Anyways, I hope this helps and have a great